Hello everyone, welcome back to Calculus. We will continue to work on section 3.9. It's about derivatives of exponential functions and logarithmic functions. We already covered about exponentials. Basically, there are two rules, or really, to be precise, just one rule. But anyway, let's say there are two rules. The first one, very simple. The exponential function, it is the only one such that the derivative is itself. And more likely, I guess you want to know a little better more about the second rule, the simple rule combined with the chain rule. Okay. So derivative of e to the power of a function would be the derivative of the exponent times the same exponential term. Okay. And mostly, as we said in class, we consider the exponential function. It is the exponential function with base e. But anyway, I suppose you also can handle the derivative with base other than e. So this is the derivative formula for exponential function with base other than e. And also we did those examples. So I'm not going to repeat all the examples for now. And mostly for this part, we are just moving to the second formula, the second part of the section 3.9, derivatives of logarithmic functions. And similarly, when we consider exponential functions, usually it's about the exponential function. And for logarithms, for class purpose, mostly we consider the natural logarithm. It is ln log n of x, natural logarithm. So accordingly, the derivative, somewhat surprisingly, it's just 1 over x. It has nothing to do with exponentials or logarithm anymore. Okay. And the derivative log n of x, it is 1 over x. And then another quick example I just want to mention. What would happen if we have logarithm, not the natural logarithm, logarithm with base 2, base 3, or any base b? If that is the case, I just want you to know mathematically, we always can convert a logarithm into the form of natural logarithm. Log b of x, it is log n of x over log n of b. And similarly, if you look at this formula, you may say, okay, a single logarithm, it is converted into logarithm. That's more complicated. But anyway, it's really not the case because usually this b is a fixed number, like 2, like a number 3. So what you can consider here is it is 1 over log n of b, this entire thing. Log n of b in the denominator, it's just a constant, it's a fixed number. And then that's the natural logarithm of x. Okay, that's what I said. A logarithm with any base always can be converted into the natural logarithm. Accordingly, the derivative of logarithm with base b of x, it is 1 over log n of b times 1 over x, or simply it is 1 over log n of b times x, the entire thing in the denominator. Derivative logarithm. So it should be simple and easy enough, right? And again, you want to know this new rule very well, and also you need to combine the new rule with all the older rules, like the product rule, quotient rule, or chain rule, those things, okay? So specifically, I do have the simple rule combined with the chain rule, derivative of log n of a function. It is f prime over f. Log n of a function f, it is f prime over f. For example, if we consider derivative of log n of 5x squared minus 7x plus 4, please follow the formula carefully. Okay, the formula says f, it is right here, okay, the function inside the logarithm. So I just copied on the function as it is. And then the top, it is the derivative of the denominator related 10x minus 7. I suppose this should be easy enough, right? And the thing about logarithm here is, well, as I mentioned earlier, logarithms and exponentials, they come together, really. When we work with logarithms, we need exponentials, or when we work with exponentials, we need logarithms. And also exponentials and logarithms, they do have some special properties. So specifically, I want to review a few properties, or maybe those are called laws of logarithms. Log n of a product can be separated into two logarithms. I'm writing the property, each property, just using natural logarithm. Okay, you need all the rules, properties, the laws they work for any logarithm. But anyway, as I just said, any logarithm just can be converted into natural logarithm. Okay, log n of x times y is the same as log n of x plus log n y. Log n of x over y, it is the same as the difference of those two logarithms. Log n of x to the power of r is r times log n of x. And in particular, I want to take a quick look about those two properties, first two properties. Okay, would it make sense to you? I'm looking at the first property. Okay, the logarithm of product, it is separated into sum of two logarithms. So as I'm saying, would it make sense to you? And using this property, this logarithm property, really somewhat it is converting a product into a sum, right? X times y into sum of log n of x and log n y. And the second property, indeed, it is converting a quotient into a difference. The reason I want to mention the converting from product to a sum, the quotient to a difference, remember in the calculation of derivatives, we do have product rule and the quotient rule, right? Somewhat I really have to say, oh, I guess you have to agree with me. It's somewhat, it is more complicated to consider product rule and the quotient rule for derivatives. So hopefully, if you know properties of logarithms or laws of logarithms very well, there's a good chance, if you have to deal with the product and the quotient, they can be converted into sum and the difference. So I have one more example for this part of the discussion. Let's say if we want to consider the derivative of this logarithm. It's pretty much complicated, right? Logarithm of a function, and then if you remember the formula, it's right here. Yeah, it's right here. Derivative of log n of function, it is f prime over f. F is fine in the denominator. Whatever the f is, it's right here. It's inside the logarithm notation. The thing is about f prime, and then you look closely about what f is. Okay, we put this in the denominator. Then for f prime, do we need to calculate the derivative using the product rule and the quotient rule? And there's chain rule involved, right? Because of square root at least, really. There's product rule, quotient rule, chain rule, mostly. All the rules involved. And I will say it might be very much complicated. But anyway, if you figured out if it doesn't make sense, what I said a moment ago, using the laws of logarithms, okay, we can convert a product into a sum, a quotient into a sum. Okay, so what I did here is I'm looking at the derivative of this entire logarithm. I really did not calculate the derivative yet in the beginning. I'm just considering this logarithm because in the first way, this logarithm can be considered as a quotient, right? Logarithm of quotient. So it can be separated in difference of two logarithms. And then also for the numerator part, it's a product, right? Logarithm of single product. So it can be separated into two logarithms. And somewhat I just skipped the little, well, skipped a little bit here. I just say the logarithm of this entire thing indeed can be separated into the sum and the difference of those logarithms. And then after converting the product and the quotient to sum of the difference, at least I hope you understand, to make this conversion, such a conversion to happen, now we don't have to deal with the product rule, right? We don't need to use the product rule, quotient rule at all. And furthermore, if you recall, there's another property of logarithm. There are three laws I listed. When you have logarithm and exponential combined, usually it can be simplified. It's just true. Log n of x to the r is r times log n of x. So log n of x to the 11, it is 11 times log n of x. And this cosine to the fifth power really means the cosine of x, the entire thing to the fifth power. To the fifth power, okay. And then log n of square root, well, you may want to say square root, that's not a power, but I hope you still remember. When we have square root, we really, in calculus, we consider that is to the power 1/2. So that's a power of half, 1/2 here, okay. And then using this third property, third law of logarithms. Log n of x to the 11, it is simplified as 11 times log n of x. Log n of cosine x to the power 5. I just realized this 6 really should be 5 here. Should be 5. And this log n of square root, after converting into the power of 1/2, we could take down this 1/2 as the coefficient for the logarithm. And then I suppose it makes the direct derivative calculation a lot easier, because when we calculate the derivative of the entire logarithm, because the sum and the difference, we can calculate the sum and difference for each derivative. And the derivative of log n of x, it is 1 over x, combined with 11, it is 11 over x. And for this part, actually, I just figured out the 6 should be 5. And then derivative of log n of cosine x, derivative of cosine, that's a negative sign. Combined with this 5 in the front, that's a negative 5 times sine x. And the cosine stays in the denominator. Then derivative of minus 1/2, I think it should be minus 1 over 2 times 3x plus 2. Don't forget the numerator. We need to calculate the derivative of 3x plus 2, which is 3. So it turns to be 3 over the entire thing. The minus is still the same. And actually, I figured out I made some small corrections. And if still you see something wrong, if it's not right, please do let me know. So this part of the discussion, it is for the derivatives of logarithms. And derivative of a single log n of x, it's very simple. And also, I hope you know derivative of log base other than e. Okay, it would be 1 over log n of b times x, the entire thing in the denominator. And more importantly, you may want to know the general derivative rule for the logarithm function. Log n of a function, log n of f, it is f prime over f. And besides, you really need to know the properties or laws of logarithms, especially for the last example. Without knowing the laws of logarithms, it would be lot more complicated. Okay. I hope it makes sense. Everything makes sense to you. So if you have any questions, feel free to let me know. Thank you for watching.